Hello, today we're going to do integration by parts. So we apply this when we have the integral of two functions multiplied together generally. It might look slightly like the product rule that hopefully you recall from differentiation. So when we differentiate two functions multiplied together. And in fact, that's where we're going to begin. Okay, so let's recall the product rule that we saw in differentiation. And that's so on the left hand side here we have u and v, both functions that we wish to differentiate. And to do that we take u prime then v, so in other words differentiate the u, leave the v the same, and then we add u then v prime, which is where we differentiate the v but leave the u the same. Okay, so that's the product rule, and if we integrate both sides of that product rule, on the left hand side we have the integral of this derivative, on the right hand side we have the integral of the two sums. So on the left hand side, if we have the integral of a derivative, that kind of disappears and we have uv. On the right hand side, we're going to apply one of our rules of integration, which is the integral of a sum is a sum of two integrals. So we break those apart. We'll just rearrange this slightly. So we have the uv and we'll subtract the u prime v from that, the integral there. And so we're left with uv prime equals uv minus u prime v. Okay. One more thing we'll just sort of throw in. This is only a notation device. We're going to let du equal u prime of x dx, and we're going to let dv equal v prime of x dx. And so our formula for integration becomes the integral of u dv equals uv minus the integral of v du. And you'll notice we still have an integral here. Okay, applying integration by parts, we always have sort of one more integral to do at the end. But this is our formula, and so let's look at it more formally. So our integration by parts, let u and v be differentiable functions of x, and then this is the formula we get. So we just saw it. The integral of u dv equals uv minus the integral of v du. We can also apply it if we plug in, if we have definite integrals, so we can plug in the limits. And that really just works the same. We integrate as we've done before, and when we get our integral, we can apply the limits, the x equals b and the x equals a, to find the value of the definite integral. Okay, so that's really our theorem for today, but we'll see a couple of examples of how it works. Okay, so as I say, we have two functions multiplied together here, an x, e to the x. And probably the biggest challenge, particularly when you're doing this at first, is choosing the u and the dv. Okay, if you make the wrong choice, you can end up going kind of like down a blind alley. But with a bit of experience and with a priority list we'll see at the end, you can get better at picking the u and the dv. In this case, the u, remember, we're going to differentiate. So I really probably want the u to be the x and the dv to be the e to the x. Okay, so I'm going to pick the u and the dv there. So I'm going to take the derivative and the antiderivative respectively of those two. And so du, of course, just equals dx, and v equals e to the x. So those are our two pieces that we're going to bring into the formula. We'll bring the formula in right there and apply this. So our integral of x e to the x, right, so this piece is uv, and then this piece is v du, and so we get x e to the x minus the integral of e to the x dx. And I'd say we still have an integral left to do, but because we've applied this well, this final integral of e to the x is very easy. We know that the integral of e to the x is just e to the x. So this just becomes x e to the x minus e to the x, and then plus our constant of integration, plus our c. Notice here we still had an integral here, so we didn't need the constant integration yet. But when we got to this stage, there's no integrals left, so then we need the plus c. And that's not too bad. That's pretty straightforward. Okay, so we have another example here. We have x squared sine x. Again, we need to pick the u and the dv very carefully. And again, because we've just got this power of x here, I think we'll pick that to be our u. And I hope that it'll get a bit simpler. And then we'll pick our sine x dx to be our dv. Our du, just 2x dx, and our v is going to be negative cosine. Be careful with the negatives. Again, maybe we'll just bring the formula, and so we get u times by v, be here. And then we subtract the integral of v du. So it's these two terms. You'll notice here we have a minus minus, so let's just fix that, make that a plus. And so sure enough, we've reached this stage. But still the integral here is still pretty complicated, right? It's still two functions multiplied together. So we are going to have to apply the integration by parts just one more time. Now you can sort of keep track of this as you're going along. I quite like to sort of go separate and just break this apart. This is kind of scratch work on a side somewhere. So now we have the integral of that final piece, the 2x cosine x. Again, we're going to pick the u to be the power of x, in this case 2x, and the dv to be the cosine x. Now our du is just 2 and our v is sine. And so again, applying our rule, we get that the integral of 2x cosine x is 2x sine x minus 2 sine x. And then finally, of course, we still have an integral, but this time it's a pretty straightforward integral. So that integral, the 2 sine x dx, just becomes 2 cosine x when we integrate. And again, we'll throw in the constant of integration at this point. Okay, so bringing it all together, this is what we saw previously. This integral we just took, so we'll pop it up there. That's kind of scratch work. And so our integral becomes negative x squared cosine x plus 2x sine x plus 2 cosine x plus that constant of integration. And sure enough, that's our integral. Okay, so we had to apply integration by parts a couple of times, but that's okay. Also notice you can kind of see we had x squared here was our power of x. In theory, we could just keep increasing the power of x here and do it a bunch of times. Now, in practice, of course, that would be hard to do over and over again, at least by hand. But at least theoretically, we'd know how to do that. And maybe we could spot a pattern. Okay, now here's our final example. Now, this is going to work out slightly differently. We've got an e to the x sine x. So again, it's two functions multiplied together, so we can apply integration by parts. Now, I'm going to race ahead. I've picked u equals e to the x and dv equals sin x dx here. And I'm not going to put in all the steps. We'll just race straight ahead to the next step. So we get negative e to the x cosine x plus e to the x cosine x. Okay, well that doesn't feel like we've made a lot of progress. Okay, the e to the x cosine x is much better than we started with. However, we'll stay with it. We'll apply integration by parts again. And the important step here is, previously I applied u equals e to the x and dv equals sine x, and I want to be consistent with that. So I'm integrating this second piece. I'm still going to pick u equals e to the x and dv equals cosine x. Again, I'll skip the steps, but let's bounce straight ahead to here. Okay, so we've got the original integral is equal to negative e to the x cosine x plus e to the x sine x, and then minus e to the x sine x integrated. Well, this looks kind of familiar. In fact, this is what we started with. This is exactly the same as our original integral. So in some sense, it feels like we've made no progress. Okay, we've got literally back to where we came from. But let's just tell you what, to simplify this a little bit, let's set I equal to that integral. Okay, so if I is equal to that integral, we get that I replaced here and I replaced here is just, so the I is equal to negative e to the x cosine x plus e to the x sine x minus I. And in fact, if we were given this as an algebra problem, this is very easy. Okay, we take the I over to the other side, so we get 2I. Just a little note here, you'll see I brought in the plus c here. Well, on the line before, we still had an integral here, but we don't anymore, so we do need the plus c. But we've solved for the 2I here. And so if we want to solve for I, well, simply divide by 2. Again, a little note, kind of feels like I've cheated by not dividing the c by 2, but since it's a constant integration, it really doesn't matter. If you want to call that c over 2, that's fine. But we finished. Remember, we said what I was. We said I was this original integral. Therefore, we've found what I equals. So that is the integral of e to the x sine x. It's simply negative e to the x cosine x plus e to the x sine x all over 2 plus our constant of integration. That's a pretty neat trick. Okay, we have these e to the x's and these sines or cosines. We know they kind of cycle. E to the x differentiates to itself. The sines and the cosines cycle through with negatives coming in. So anything we look like that, we'll apply it a couple of times to hopefully get back to where we started from, and then we can solve that integral, and just like we did here. Okay, so that's great. Now I mentioned just one more trick here is picking the u. Okay, obviously if we pick the u, we sort of by default pick the dv, and there is a priority list for picking that u, and it has a little acronym which is LATE. Okay, so first of all, if we're looking to pick the u generally, we should look for logs. So we're going to pick u equals natural log of x, and that's because the derivative of the natural log is fairly straightforward, where the antiderivative is not. Our next choice for u, if there isn't a natural log, is some sort of algebraic expression, in other words an x squared. Then we go down to a trig, so a sine x, and then we go down to an exponential, for example, e to the x. Okay, so that's our priority list for picking the u. And of course, once we pick the u, we've also sort of by default picked the dv. Okay, so I'll say we apply this integration by parts whenever we have two functions multiplied together we wish to integrate.